The next speaker is Kathleen McDonough from Procter & Gamble. She's also the organizing committee member. And so she's going to present on the role of biodegradation in reducing microplastics in the environment. Kathleen.
Thanks, Anil. Happy to be here today. So in all honesty, just to let you know, this talk actually came out of a series of discussions we were having as we were planning the workshop. And it seemed as we were getting on the phone, the question of whether biodegradation was a good option and when it was a good option came up repeatedly. And we had a number of very interesting discussions about it. So we thought it would be pretty interesting to bring it forward today and to bring up some different scenarios and look at some information that we have on biodegradation and when it can be helpful and there's a reduction in this space and when maybe it won't be as helpful and we need to make some decisions about it. So trying to think about infrastructures, trying to think about end of life of materials, trying to look at this holistically and saying where is there value and where is there maybe not as much value. So we learned yesterday, that this is a really complex problem. We've got primary microplastics, we've got secondary microplastics, we've got a lot of different compositions of materials that we're talking about, different shapes, different sizes. How they're used will basically depend on, how they're used will then see how we end up in the environment, right? So are we using these in a material that's going to end up down the drain? Is it already a primary material that's very small, less than 5 millimeters, and it's going to go down the drain to wastewater treatment in an infrastructure that exists already, that is actually there to help for biodegradation, right? We have wastewater treatment for biodegradation to occur. Or is this going to have a widespread use such that it's left in the terrestrial environment? And we heard some of that yesterday. Or is this a plastic bottle that potentially we could collect in developed countries where there is a system for collection? But what if we're in undeveloped countries, as we just heard about? There's not a system for collection. What is the right alternative? And so as we're thinking about this issue of biodegradation, we shouldn't apply it blindly, and we shouldn't walk away from it. We need to really think about where there's value. So I thought I would take us through some case studies. But before I do that, I do want to kind of ground everyone in when we talk about biodegradation, because we do find there's some confusion here. So if we think about the secondary microplastics, they start as a plastic in the environment. Say, let's talk about the bottle, right? So we've got that whole bottle. And what happens is that whole bottle actually goes through weathering processes, and we've heard about some of those yesterday. And it breaks then into fragments. And that's really going to be the first step of breaking down that bottle. There can be a biofilm growing on it. It can have wind erosion. It can have photodegradation occurring. All of these things that break it into fragments. Those fragments then need to biodegrade. And then or we have the primary microplastics that start as small materials that we need to biodegrade. When we talk about biodegradation, we're actually then talking about that material, the carbon that is in that material, your organic carbon, being converted into CO2, all of the other portions into water, small molecules that are left. It's completely converted by the microbial community. And as I talk today, that's what we're talking about when we talk about biodegradation. We're not talking about something fragmenting into small pieces. So one of the first examples I wanted to take you through is one of the first issues that we saw come up with microplastics, and we heard a bit about this yesterday, and that was the microbeads. So if there are microbeads that are used in a shampoo or a face wash, and that's going to go down the drain if you're in a developed country to a wastewater treatment plant, is there value in having alternative materials that are biodegradable? And are they actually biodegradable? There was much of this discussion occurring a few years ago. And so one of the things we wanted to take a look at in our lab was, okay, if we are saying these are good alternatives, are they really going to biodegrade? And so we put them into some standard biodegradation studies where we used inocula from wastewater treatment plants as our microbial sources. And we looked at the ability of some of these materials to biodegrade. So if we take a look at these types of materials, we're talking some of the alternatives were some of your wax-based materials. So beeswax, jojoba beads, stearyl stearate, and one other wax, rice bran wax. And then we also took a look at some synthetic particles, and those are PHBV, polyhydroxybutyrate valuate. Those of you familiar with replacements for plastics see this material around a lot. It's one of the lead materials for a biodegradable alternative in the space of plastic. So if that is made into a small exfoliant form, can that biodegrade? And then we took a look at some of the other materials that were being looked at as replacements that are natural materials, blueberry seeds and walnut shells. And we just said, all right, let's take a look what biodegrades, what doesn't over the course. We ran the study out for 80 days to see what could actually biodegrade. We found out that our waxes were pretty biodegradable. So beeswax, sterile stearate, rice bran, back to jojoba beads, they all can biodegrade pretty well. And the PHBV synthetic material actually biodegraded on par with those waxes as well. So all of them had a very good biodegradation profile, reaching very, very high extensive biodegradation. I should mention to you all, in this study, we're following carbon. So we're measuring evolved CO2 in these studies. We know how much carbon we put in the system. The carbon is the only food source present for the microbial community in the system. And so as it breaks down the carbon source, it evolves CO2. Because it's actually a live biosystem, you're actually generating CO2 for energy, and you're converting some of your carbon to biomass. So you're never going to reach 100%. You reach about 70%, 80% in these systems, and it depends on the chemical, and it depends on the microbes, and how much that microbe actually converts to CO2 versus how much it moves into biomass and growth of new microbial communities. So, just to explain that graph a little bit for y'all, that's the kind of data you see when you're looking at these types of studies. So what was my evolved CO2 over time? So the jojoba beads and the waxes and the rice bran wax all did well. Blueberry seeds, they were biodegrading. They're just a little bit slower, and that's what we saw. We still were up an upward climb in the study after 80 days. They just were a little slower. They had reached about 40%, and walnut shells did not go at all in this study. And that's actually been seen in some other studies as well. So that's interesting. So we had some discussion yesterday about the growth of biofilms, so I thought you all might like to see this picture here today. So if you expose, this is your jojoba beads when you don't expose them to any microorganisms, and this is when you bring them in and expose them to activated sludge. And so what you see, this is kind of a biofilm. We heard that talk about yesterday. When you look under the microscope and you start looking at the microorganisms present and looking at the biofilms grown, it's pretty interesting to see. It's tough to get some good pictures to show you, but you can see the black growth on there is a biofilm. And then what you see is these particles. It's a surface-mediated process, and you're breaking down from the carbon from the outside in. And so you actually can watch it happening, which is different for those of us who do biodegradation work. Typically, it's with chemicals and things. You don't actually get to watch it happening. But here we can grab samples, look under the microscope, and actually see what's happening as they're biodegrading away. And it's a surface-mediated process. So that actually then led us to say, well, for these materials, in this space of a microplastic, in this typical size range that we see for replacements of exfoliants, where we're at 100 micron up to a few millimeters, how much of an impact on the size of the material, even in this small size range, will there be on the biodegradation in these types of studies? So we took our beeswax, which we knew was biodegradable, and we ran a study where we looked at a bunch of different size ranges from 94 microns up to 3 millimeters. And we wanted to see what would be that impact on the rate. And essentially, this is a surface-mediated process. You grow a biofilm, so of course there's going to be a big impact. There's a lot more surface area when you've got small particles than when you've got one large or two large particles that you're putting into a study. And that's exactly what we saw happen. And we saw a direct relationship with the available surface area to the biodegradation for these materials, even in this small range of 100 microns to 3 millimeters that we expect to see in the size range of these microplastic materials. So the reality is these types of materials, exfoliants that are used in face washes and things, that's a widespread consumer use. It can go down the drain. It can go into an aquatic system if it's not going in a developed country to a wastewater treatment plant. So there can be a real value for biodegradation to occur, because how are you going to collect that? It's going to be almost impossible to collect that. So if biodegradation can occur, that's a real value, and we should consider that. But what about one of our other issues that we talked a lot about yesterday? So what about the textile fibers? So textile fibers, again, in a developed country, these can go down the drain through wastewater treatment. In undeveloped countries, they may go straight out into aquatic systems. Is there a value in having these fibers be biodegradable? Is there ways to collect them? There has been some discussion about that, and there is some work being done. I think some of you probably have seen some of the articles where folks are trying to develop filters for the ends of washing machines. But again, there's different practices in different parts of the world. So in our undeveloped areas, there's not even a washing machine. So the filter on the end of it isn't going to collect anything because you don't have a machine there. Then we heard yesterday that there's some new work to look for having fibers not come off of clothes. Maybe that's an alternative as well, right? Alan told us that yesterday. But let's take a look at what biodegradation can do to help us in this space. So this was actually a nice study done by the folks down at NC State. And they took a look. They wanted to know that using the microbial community from activated sludge wastewater treatment, so the dominant treatment in developed countries, would they see biodegradation from these fibers occur? And so they took a look at cotton, rayon, and polyester, and then a mixture of cotton and polyester. And they essentially saw what you might expect, your cotton materials and your rayon. So rayon, for those of you don't know, is a form of a cellulose as well. It's a modified cellulose. So these are all really cellulosic type materials that biodegrade pretty well in general. And so they actually did see biodegradation of their cotton, their rayon, and also their blend of polyester and cotton. But their polyester didn't biodegrade at all. Their blend is the one here in the middle where it looks like basically the cotton was able to biodegrade even though it was blended with the polyester. So actually, in the form of these fibers, there could be some value. If we can't collect them well, there could be some value in biodegradation. Now, I will note, and the authors did note very clearly, they did not get into the influence of dyes and additives that are used in some of these fibers, and they said that that was further research that they needed to be doing. So these were clean fibers that they used. But it is interesting to think about. There could be an option there that is valuable in that space. What if we make sure that our dyes and additives are biodegradable as well, and they're not impacting the biodegradation of these materials? Then all of a sudden, maybe we have alternatives in the fiber space that are biodegradable. So just something to think about. And we heard a little bit yesterday about the agricultural space as well. So we know that there's use of plastic-type solid form materials in the agricultural space. So one of the uses is in controlled release fertilizers. So those of you that aren't familiar with these technologies, essentially what they're doing is this allows the farmers to apply fertilizers. They actually apply less fertilizers, and they do it in a way that allows, there's a time release element to it, and they then release the fertilizer at the right time, and they actually then use less, which is better for the environment, right? Well, if we have a capsule wall that remains and is not able to biodegrade, then is that an issue for us in the environment as we figure out the size range of the environmental impact of these materials? Are we going to be able to go back on the farmland and collect these? Probably not. This is widespread dispersive use. How are we going to go collect these? So there could be a real benefit in having biodegradable wall materials that are gone. But that's tricky. We need it to last long enough to be in place to hold that fertilizer, but then when it releases, it has to biodegrade. Now, I know there's a lot of active research. If you take a look in the literature on this, it's not an area that I'm actively researching in, but there's others that are actively researching in this space, and it's a pretty tough problem. All right, plastic bottles. So here's the big one, right? This is the one everybody talks about. This one's tricky. So we heard from Rebecca about the issues in the developing countries. We don't have an infrastructure in place. So what are we doing about all of this solid waste that's going out there? Is biodegradation a good option? But in developed countries, we do have infrastructure in place. We can collect. So then is it society that we have to change and their habits for collection? And then do we have to find value from what we're collecting such that we talk about upcycling, which we'll hear about next? What is the right what should we do? And so we have to really think through these problems holistically. And so if we take a look, I thought it would be interesting to take a look at a case study material. So I mentioned PHBV. It is one of the leading biodegradable options, and we know more from studies on this plastic alternative material than many. And so if you take a look at some of the work that's been done, there's been quite a bit. There was an early study done a number of years ago, 1992, where some folks went out and took some films in some bottles that were made of PHBV, and they hung them in a river in Switzerland. 6 degrees C, very cold, not all that conducive for the microbes to be working very quick. But they actually took a look and said, could the PHBV biodegrade? And what they found was that the films were completely biodegraded over 250 days that they left them out in the field. But the bottles didn't biodegrade as quickly. They only found around a 10% mass loss of the bottles. And so then we said, well, that's all that's happening. They've got it hung down in the water. They didn't have a lot of other processes helping with weathering. And so they said this is kind of a slow process. But then there's been more studies. There's been other environments, and there's been some other groups that have hung some bottles and films and all sorts of things out in the environment, and there's been a lot of lab studies. And so actually there was a nice review by Dilks and Hoffman just recently, where they tried to bring together all of the data that we had on PHBV. It's a surface-mediated process. So how much do we know about its biodegradation? Can we actually come up with a relationship between the surface area that's available and the biodegradation rate? And then we start using that to estimate for different materials, will it biodegrade and how long will it take, based on our best knowledge from both lab and field studies. And that's essentially what they took a look at. And they estimated that the plastic bottle would take between 1.5 to 3.5 years to biodegrade on average from all of the studies brought together. So is that fast enough? Right? That's what we're stuck asking. Is that fast enough? If we don't have if we're in an undeveloped country where we don't have a collection system, is that a better alternative? And that's what we really have to struggle with. Should we be putting our time into that, the money into that development, or should we be focusing on infrastructures and collection systems and other alternatives? And I think this is what we'll be grappling with this question as we try to figure this out. Tire wear, we had this discussion in detail for my planning committee members. What do we do? Do we need biodegradable tires? I don't know. What do you guys think? If you need your tire to last longer, you have to go out every morning and spray antimicrobial on it. Is that right? So what do we do? It's a tough problem. Tires are meant to be stable, right? Wow, we're driving at very high or low speeds, depending, and we are subjecting this to lots of friction and temperature changes, right? These are very stable materials. In general, it's hard to get very stable materials to then biodegrade. So is that really an option? This is going to be widespread use, though. How are we going to collect these tire materials? Is it a good option that they biodegrade? It might be pretty tricky to get there. It might not be such a good option in these materials. We're worried about inhalation. If it's a direct exposure for inhalation, and we think that might be really dominant from what we heard yesterday, does a biodegradation in an aquatic or on a terrestrial, that might be a secondary process to that initial exposure from an inhalation. So does that help us in this space? So we really are going to have to think through all of these questions before we go and develop our biodegradable tire, and whether that's really going to be our best solution, or do we need a tire that's completely stable, nothing can come off of it at all? Is that the flip side to go? But then it's never, ever going to break down, right? So this is really a tricky situation. So hopefully that stirred some thoughts for everyone, and we can have some interesting panel discussions about the right path forward and the right way to think about the end-of-life processes of these materials, the environmental fate, what's going to happen to them, what is available from infrastructure. Is biodegradation a good option? Is it not? And hopefully we can bring all these together and make some good decisions about all these different classes of materials that we need to deal with. So thank you.
Yeah, if you can stay here just for a minute. There are some questions online. And then maybe some questions in the room. We still have a lot of time. Do you have data on gut microbiology to degrade microbeads after ingestion and enterohepatic circulation?
So we by microbead, again, are we talking alternative materials or are we talking a traditional PE material? Those materials have not been shown to degrade very readily, and in studies that we've done have not seen them go in the types of systems that we've been doing. So if you're talking about those traditional materials, no, we have not seen them go in these types of studies.
On the second question.
So an OECD 301B is a standardized test method. I'm sorry, let me read the question to y'all. I'm processing and ignoring you. Okay, so the question is, what was the temperature of the inocula in the 301B test method? And in many cases, they are done in ideal conditions at 20 or 30 degrees Celsius. Okay, so the OECD 301B test method. So this is a standard biodegradation test method. And how it works is that you actually you've got a nice mineral media that can support the growth of your microbial community. And you put in a very low level of microbes, about 30 milligrams per liter, and you put in about that same amount of your test chemical. So this is not an environmentally relevant situation. From regulatory purposes, this is typically called a screening test, because it's not environmentally relevant. You're at a very low level of microbial community, a very high level of your test chemical. But you have to do that because you're following carbon. Your analytical method is not going to allow you to get to an environmentally relevant concentration. That's just how it will be for this type of test. So when we run these tests, that's the situation. So that you run these tests at 20 degrees, and that's common in the test methodology. I believe it's 21 plus or minus 2 degrees. And this was a standard test. But it is a conservative screening test, and we do know that from our history of work with chemicals.
Any other questions in the room? Yeah, please.
Hi. Quick comment and a question. Yeah, I agree with you. I think there's a lot of confusion around the OECD test, right? It's meant to, the 301 particularly is meant to be sort of unequivocal, right? A pass is so stringent that it's meant to be unequivocal. But I'm really glad you brought up the issue of sort of use and reference materials. And right, so the typical criteria in the past for ready biodegradability or rapid degradability is very much a soluble chemical criteria, right? And the idea is you have chemistries that degrade very fast. You have the sodium benzoates of the world, so that's what you compare it to, right? Mm-hmm. And so for these types of materials, I think we need to ask the question, what should we be comparing it to, right? Is it use specific? So for the slow release fertilizers, that's a very good question, right? It needs to last for a while to be useful, but if it lasts shorter than traditional materials, or if there's some sort of reference that we can base it off of, and similarly for the fibers, if cotton sticks around for a year, right? Should we be basing our sort of assessments on these materials and these new materials, not only on the time they spend in the environment, but their total life cycle assessment, and right, do we need to take a more holistic approach than we maybe have in the past with soluble chemicals?
Yeah, I definitely, as I was discussing today, think we need to be really thinking holistically about all of the impacts and all of our choices in this space. In terms of reference materials, I agree, and especially think about the size and shape of the material, right? You should run a reference material that is similar in size and shape to what you're evaluating, or else you could be getting completely different results of a material. If you run a very small molecular weight soluble material, it's widely dispersed in the system, more easy for the microbial communities to biodegrade than if you have to grow a biofilm on a solid material and work your way in based on surface area. And that's the reality of how the biodegradation will happen in these. Good point. Thank you.
Thank you.
Maybe we'll take
Please.
one question and then go to the panel, and then please go ahead.
Thank you. I just wanted to point out that, when you showed the data that film was able to, when it was put in the river, it was able to be consumed, but bottle did not. I think, was there a difference in thickness? And, if, thickness is a criteria, even a thick piece of wood, if we put it out in the environment, it will take long to be consumed. So do we need to look at these bio-based plastics in a different light? Because they start getting consumed from outside to inside.
Definitely. I mean, definitely the size and the shape. We need to be figuring out the processes. So if you're talking about a larger material breaking down, we need to be accurately simulating those processes or getting out in the field and actually seeing the time frames for these disintegration processes, the weathering process to actually occur, and understanding then on top of it the time for the mineralization process to occur, the biodegradation. So I agree. Thanks, Amir.
Thank you, Kathleen, once again. Excellent.